So today we're going to continue to discuss compressible flows. And again, the motivation is how the aerodynamics changes dramatically as the Mach number increases from around 0 to something comparable to order 1, right? So let's first review what we did in the last lecture. So we started from actually two very fundamental thermodynamics equations. One is P, the pressure is proportional to the density times temperature, right? And the second thing we started with is basically how the heat capacitance under constant pressure is equal to a constant gamma, which is equal to 1.4 for air times the heat capacitance on the fixed volume. So both actually had something to do with the microscopic interpretation of what temperature is, right, in ideal gas. It's really just a measure of how much kinetic energy the gas has. And so the kinetic energy actually translates into pressure because as the velocity increases, right, there are more molecules hitting the wall, and every time a molecule hits the wall, it transfers more momentum. So there is a squared relation with that, with the velocity. So is temperature. Another thing is that there are multiple degrees of freedom in kinetic energy. There is not only linear motions, but also rotational motions. And for air, most of the molecules have two atoms. That means the kind of rotational motions are constrained. So the heat capacitance for ideal gas with two molecules versus more than two molecules are different. So fortunately, we don't have as much carbon dioxide in the atmosphere yet, and the heat capacitance is pretty much the same as any gas with two atoms composing its molecules. So these are the two equations we started with, right? And then the first thing we derived is that as we use the calculus, we use the proportional change, right? We call fractional sensitivity, to derive that if I change the density by a little bit, right? If I increase the density by a small fraction, and I represent the fraction as d rho over rho, the pressure is going to be changed also in a proportional way, and the proportionality constant is exactly this gamma, right? So that's the first thing we derived based on these two equations. And then what's more interesting is that we combined this equation with an equation that's basically Newton's second law, right? We combine this equation with u times du. So u times du in a steady state flow is actually the acceleration, right? Is actually du over dt, where the d means a Lagrangian derivative, the derivative of time when you are tracing along a fluid particle. So u times du, the acceleration, is equal to minus dp over rho. So that's basically, again, acceleration, because dp, right, actually, both has to divide it by dx to actually get the unit of acceleration. So dp over dx is the pressure gradient. It represents the pressure force per unit what? Volume, right? Per unit volume, right? So okay, so yeah, I think we derived it by basically taking a volume and saying, okay, pressure times the area, right, is equal to force, and therefore delta pressure divided by dx is actually gets into the force per unit volume, and then divide by another rho. So the division by rho changes the force per volume into force per mass, right? And that is acceleration. So this is the equation. This is the second equation we used. So this equation, right, without the dx, we combined with this equation to derive something quite remarkable. That is how the density in a compressible flow changes as the flow accelerates. So what we derived is d rho over rho, the fractional change or percentage change in density, actually is related to du over u, the fractional or percentage change in the velocity. And that relationship turns out to be, first of all, it's minus, right? We accelerate, the pressure drops, the density drops. So we have a negative sign over here. And the proportionality constant turns out to be the square of velocity divided by gamma times p over rho. And we called this constant, this proportionality constant, as the square the Mach number, right? It's actually not a coincidence. We're going to find out when we go into acoustics that the denominator over here has, of course, the unit of velocity squared, and it is actually the square of the speed of sound. All right. So this is what we got in the last lecture. So today we're going to start by using what we derived in the last lecture and look at we already know how density changes upon acceleration. Now let's take a look at how pressure changes upon acceleration. All right. So this is actually simply a combination of the equation we derived and this relationship between fractional change in density and the fractional change in pressure, right? So as a result, we have dp over p is going to be equal to not minus Mach squared, but minus gamma times Mach squared times du over u. All right. So the pressure changes in an even more sensitive way than a density change to acceleration. Okay, so let's actually start by using these two equations and look at an example problem, right? We might be asked when examining aerodynamics of something. So let's say we have a uniform free stream. It enters a slight contraction. By a slight contraction, I mean a contraction in percentage of the area. The area reduces by a small, let's say, X%. Okay, so first of all, let's actually answer the question in a scenario we are already familiar with, right? So if the flow is incompressible and inviscid, how much does the pressure coefficient change? Right, we know the pressure coefficient is 0, right, in free stream. So this slight contraction, so Cp is equal to 0 at free stream at u infinity, right? Now we have a X% reduction in the area. So how much? What is the Cp downstream? How do we start thinking about this question? For incompressible flow, what do we use? Yeah.
Use conservation of mass, and then well, that relates to the area, right? Because density is constant.
So we first use conservation of mass, right? So that's actually half of this answer, right? The other half, think about it. I'm going to first write down the conservation of mass. So for conservation of mass, rho times u times a is constant, right? All right, and rho is also constant. That means u times a is constant, right? So if a is reduced by a small X%, u has to increase by the same amount X% if x is small, right? So that square of x can be neglected from the equation. Okay, now we're not looking at how much velocity changes, but how much pressure changes, right? What's the second piece of the puzzle we want to use for incompressible flow? Yeah, Bernoulli, yes, right. Okay, so in using Bernoulli, we know that a delta change in the pressure, right, is equal to the negative of a delta change in half of rho u squared, right? Okay, and now we are looking at a small change. So the delta can be thought of as infinitesimal. So for infinitesimal delta, we can use calculus, right? And the rho is constant. So using calculus, we pull the rho out, And a delta of half u squared is equal to u times delta u, right? So let me just write as a small delta u. We are looking at a small change over here. So let's actually replace all of these deltas as small deltas so that we know we are looking at a small change. All right. Okay. Now, finally, we're not looking at just the pressure, but looking at a small change, looking at the Cp, right? What is Cp? So Cp is equal to, or delta Cp, right? And we know the previous Cp is equal to 0, so delta Cp is actually Cp, is equal to the delta P divided by a half of rho u infinity squared, right? Okay, and of course, since the velocity change is small, we can just use u infinity here as the u in the previous equation. So plug both in. What we get is minus, the rho cancels out, the u infinity cancels out in one of them, and the half in the denominator becomes 2. What we left is delta u over u, right? Got it? Okay, so how much the pressure coefficient changes in this scenario is just the -2 times the fractional or percentage change in the velocity, right? So which is equal to increasing x%, that's just the minus 2x%. All right? Okay, so if the area contracts by a factor of, let's say, 1%, we know the Cp is going to be 0.02, right? Minus 0.02, yes?
So my question is, why or how are you defining the x%? Because the UA is, like, the product is constant. So if you increase, I don't know, A, if you would decrease A by 50%, then you would increase by something.
Yes, that wouldn't work anymore, right? So if x% is a large contraction, a large percentage, that wouldn't work anymore. So that is why the problem states a slight contraction with a small area reduction, right? So so this is the simplest scenario where we can directly use the differential form of the equations. We're going to show slightly later how to actually do integration and deal with a large area reduction, right? So the simpler form actually works with a small area reduction. All right? Yeah, good question. Now let's get to the real question for this lecture. So if the flow is still inviscid, but has a Mach number m, which is greater than 0, how much does the pressure coefficient change? So, okay, so you can still use mass conservation. That didn't change, right? But now you have to consider the effect of a change in U. That's the first difference. The second difference is cannot use Bernoulli anymore, right? Bernoulli doesn't work anymore. So we need to use something else to figure out how the pressure changes. And let's see how do we do that. And particularly, we're going to be using what we derived previously, right? That's kind of you can think of this equation as a differential form of the alternative of Bernoulli's, right? So we'll see how that works. Okay, so first of all, how much does the pressure coefficient change? So let's just copy the equation we had in the previous slide. dP over P is equal to minus gamma times m squared times du over u, right? Okay, so that's what we have. And we also have rho u times A is equal to a constant, the same mass conservation we had previously. And let's see how changing the Mach number from 0 to m changes both. So first of all, this constant equation can be written as a small delta, okay, of rho times u times A is equal to 0. And let's actually be consistent and use that small delta to represent the difference between downstream and upstream, right, which has rho infinity, u infinity, and the unchanged original area. Okay, so this equation, if you divide it by rho UA itself to represent it as a fractional sensitivity, right, things actually gets a little bit easier, because a small change divided by itself is actually equal to the small change in the logarithm of that quantity. All right, so this is actually equal to a small change in the logarithm of rho times u times a, which is log of u plus log of rho plus log of a. And that, if you expand it, becomes delta u over u plus delta rho over rho plus delta a over a. Right? Okay, so a small change in the area, which is a reduction of minus x%, right, means that delta u over u plus delta rho over rho has to be canceling this minus x%, which means they have to add up to exactly x%, right? Okay, plus we previously derived not only the pressure equation, but also an equation that tells us how the density changes as velocity changes. So d rho over rho is actually equal to minus m squared times du over u. So these two terms, sorry for the typo. So this is actually d rho over rho, not d rho over u, right? So both can actually, so we can change this d rho over rho to a minus Mach number squared times du over u, which means the left-hand side becomes what? 1 minus Mach number squared times du over u, right? Make sense? So now what we see is that upon a small contraction, right, du over u is not going to be equal to x% as we had in the previous case. It doesn't increase by just the x%, but increases by x over 1 minus Mach square %. So upon the same contraction, right, the higher Mach number is, the more increased the velocity is going to be in relative terms. All right. Okay, finally, let's plug this into the equation that tells us the change in the pressure itself. Okay, so once we plug this in, we know that dP over P is going to be minus gamma m squared over 1 minus m squared times du over u, which is x%. All right, good. Okay, so now finally let's figure out what is the pressure coefficient, right? How does the pressure coefficient actually changes? So again, the pressure coefficient is going to be the small change in the pressure. We call it, I think it's equal to the small change in the pressure divided by half of rho u infinity squared, right? And plug this in, what we get is a dP is equal to P times the whole thing, right? So what we had is the pressure divided by, let me just pull the 2 out in the denominator, rho u infinity squared, okay, times gamma m squared over 1 minus m squared times x%. All right, so did anybody see something familiar in this constant over here? Right, we previously defined the Mach number squared, right, as the velocity divided by gamma p over rho, which can be written upon over here, a velocity squared, right? So what is this? This blue circle, the blue circle 2p over rho u infinity squared is actually equal to proportional to a reciprocal, right, of the squared Mach number. So it's actually 2 over gamma times 1 over Mach squared. All right, which means we get some nice cancellations over here, right? So we plug this in, the m squared cancels, the gamma cancels. What we get is 2 over 1 minus m squared times x%. All right, that's our answer to how the pressure coefficient is going to change upon a slight contraction. So first of all, let's see a nice coincidence, well, not coincidence, agreement between the incompressible case, right, minus 2 times x%, and the compressible case. I must have missed some minus sign somewhere. Oh yes, I missed the minus sign over here. Sorry for that. So when I plug in a dp over p, there should be a negative over here, and I have a negative over here, right? So basically pressure coefficient decreases, right, upon the contraction. And when the Mach number is equal to 0, of course 1 minus m squared is equal to 1, right? So basically we get a minus 2% out of the same, out of the same geometry, which makes total sense. But what's more interesting is that as the Mach number increases more and more and getting closer and closer to 1, what happens? Right? For the same percentage, same small percentage of contraction, my pressure coefficient change becomes more and more and more, right? And up until a point that when Mach number is exactly equal to 1 or approaches 1 infinitely, my CP becomes minus infinite even upon a tiny contraction. So, well, let's just put this in the background, in the back of our head, and look at the consequence of this when we look at choking. Yes.
So, in incompressible flow, Mach number equals 0, right?
Yeah.
So, in the original definition of Mach number, how does that number equal 0, or how does the pressure not depend on the velocity?
Yeah. So in incompressible flow, right? How does the pressure actually? How does the?
So if you look at the equation below number 2, right, the one that's underlined green.
This one?
Yeah.
Yeah.
So with Mach number equals 0, you would say that pressure never changes.
So very good. When Mach number is equal to 0, what I'm practically saying is that dP over P is going to be super small, right? So what is atmosphere pressure? Roughly.
1.165.
In SI units, it's about 100,000 pascals, right? 100,000 newtons per meter squared. And what is usually, so for low speed flow, right? What is usually the change of pressure, right? You can usually compute it from Bernoulli's, right? So if you have air density of about 1, if you have a flow of even 10 meters per second, right? Multiply 1 with 10 squared, that's 100, right? So what is 100 compared to 100,000? So the ratio is going to be so small that it is practically negligible. That's what we mean by incompressible flow, right? So incompressible flow can be obtained essentially by looking at the fluid with baseline pressure so high that it is much higher than the aerodynamic pressure you have, right? So that's yeah, and as the velocity increases, the aerodynamic pressure increases, and at some point it's comparable with the baseline static pressure, and that's when you have to consider compressibility. Yeah, good question. Any other questions? All right. So, okay. Now let's start looking at a real contraction. Okay, so the question comes over that if the contraction is not infinitesimal, which is usually not the case, right? For example, if we look at the wind tunnel, the contraction we had downstairs is 8 to 1, right? That's not infinitesimal, right? So how do we, is it possible to use similar equations? The answer is yes, but you need just to do some calculus. You basically take the same equations we had in the last slide and integrate. Okay, so if you don't follow completely the calculus, it's okay. But like the conclusion, I think it's important to know that if you want the conclusion, you can derive it by going through the calculus. Okay, so what we had previously is this. So let's actually copy it down again one more time. So a change in the pressure dP over P is equal to minus gamma Mach squared du over u. Okay, so what we're going to do is to integrate. And in compressible flow, the way we do integration is that the Mach number is basically equal to 0 and the constant. So we can, the integration was pretty easy in compressible flow, right? We have dP is equal to rho u du, actually minus sign. So because rho is constant, we can just both sides of the equation just have one variable, right? One is P, one is U. So we can just integrate on both sides. The problem with this equation, the compressible equivalent, is that on the left-hand side, we still just have T. But on the right-hand side, we have two things. We have Mach number and we have velocity, right? So that makes integration hard. So what do we do? What do we do is that if we can convert the fractional change of velocity, the percentage change in velocity, into percentage change of Mach number, right? Then the whole right-hand side is just a Mach number and we can integrate. Make sense? So when the velocity increases, Mach number should also increase, right? So we should be able to get rid of du over u and represent it in terms of dm squared over m squared. Okay, so let's see how do we do that. We, of course, go from the definition of the Mach number squared. M squared is going to be equal to u squared divided by gamma. I don't even need the gamma, I just need it to be proportional, right? So for any fractional sensitivity, I only need proportionality. I actually don't need the constant, P and the rho. Okay, so like, by now, you might be already familiar with fractional sensitivities, right? So what we have is, if I take the left-hand side and look at a small change in its logarithm, which is d, that quantity d over itself, the fractional derivative. On the right-hand side, anything with the second power is going to be multiplied by 2 times du over u, right? Anything with the first power is going to be just d rho over rho. Anything with a minus 1 power in the denominator becomes negative dP over P. And anything being a constant just goes away from the equation, right? You can just derive this by taking the logarithm and do exactly what I did on the last slide. All right, okay. Any questions on this? No? Okay, then we already learned that both d rho over rho and dP over P can be represented as something proportional to du over u, right? Okay, the first term is minus m squared times du over u. The second term is, well, it's a minus of minus gamma m squared du over u, right? So the first term is just 2 times du over u. Right, so that's something we derived at the end of the last lecture. So just to combine them, what we have is 2 minus, I'm just going to write 2 plus gamma minus 1 times m squared times du over u. Agreed? So that's how a fractional change in Mach number relates to a fractional change in the velocity. So of course then du over u is just the 1 over this whole thing, 2 plus gamma minus 1 m squared times dm squared over m squared, right? Okay, so now it's time to plug this into the blue equation and keep going. So that completes our goal of having the right-hand side just being completely written in terms of Mach number. So what we have is minus gamma m squared. Underneath, it's 2 plus gamma minus 1 m squared, right? Actually, let me just cancel the m squared over here and directly write it as d m squared. Okay, questions? Just plug in this into the du over u. Right, the m squared over here cancels with the m squared over here. All right, good. Okay. Now, of course, we see a ratio, right? We see a ratio here. So what we actually do on this is to further do some change of variables. So minus gamma. And underneath here, I have gamma minus 1. So I'm going to divide and multiply by a gamma minus 1. So this becomes d of 2 plus gamma minus 1 m squared, right? Divided by 2 plus gamma minus 1 m squared. Yeah, what I'm doing is basically multiplying a gamma minus 1 here and dividing by a gamma minus 1 here. The 2 plus is going to be free, right, inside a derivative. All right, so of course this becomes a derivative of a logarithm. This also becomes derivative of a logarithm, right? So by integrating both sides, we know what comes out. So d log p is going to be some constant minus this proportionality constant times d log of this guy here. All right, good. By the way, this is usually written as because everything is inside the derivative, right? So this is usually written as 1 plus gamma minus 1 over 2 m squared, because, well, it's a multiplicative term inside a logarithm, right? A factor of 2. So it's an additive term outside of the logarithm, which in a derivative just doesn't matter. All right. Okay, agreed. Okay, so now on both sides you integrate. The result is that, of course, let me just further transform it a little bit. So this is c minus derivative of logarithm of, if you take this inside of the logarithm, it becomes a power, right? It becomes to the power of gamma over gamma minus 1. So that's just taking a multiplicative quantity outside of the logarithm into the logarithm, which becomes power. And now, finally, let's just integrate and get rid of the logarithm on both sides. So when you integrate and get rid of the logarithm, this constant, this additive constant becomes a multiplicative constant, right? So we'll just write it as proportional, p being proportional to 1 plus gamma minus 1 over 2 Mach number squared to the power of gamma over gamma minus 1. Okay, the derivation has ended. All right. Okay, I know it's a long calculus, but like, let me just tell you, if you didn't follow, it's fine, but let me tell you what this actually is. This is practically the definition of stagnation pressure in compressible flow. All right, so I think in Unified you might have already seen the equation. You might have, this might look familiar to you, right? But this is actually why this is the case. All right, okay, so let me explain why this defines stagnation pressure. This defines stagnation pressure because what we are looking at is the deceleration or acceleration of a fluid, not upon infinitesimal acceleration, deceleration, but over a finite, actually over an arbitrary length. The Mach number can go from 0 all the way to 100 or whatever range you want, right? And the pressure, as long as the process is isentropic, right? There is no heat addition or subtraction, which is underlying the assumptions we had in the equations above, then the pressure is always going to be proportional to this guy, right? Okay, what that means is that, for example, if you take a fluid of arbitrary Mach number and decelerate it to Mach 0, okay, what we find is that the pressure is going to, of course, increase, but increase by how much? It's going to increase by exactly this factor, right? Okay, so for example, if the Mach number is such that this guy inside it, by the way, this is always a quantity greater than 1, right? Okay, so if the Mach number is such that this guy is equal to 2, then by decelerating the fluid to 0 velocity, the pressure would increase by a factor of 2, right? So that is why we always, sorry, I'm missing a minus sign. So because of the minus sign here, because of, let me just write it as plus of minus, right? I mean, this is, yeah, a multiplicative constant outside of the log becomes a like to the power of -1 inside the log. So this is actually minus. Sorry. So yeah. So what I'm saying is that if you take if the pressure is such this thing is equal to 2, which means after the minus sign, this is equal to half. That means as you take the velocity decelerate to 0, right? What the right hand side is going to change from half all the way to 1. That means the pressure is going to be rise by a factor of 2, right? Okay. So that is why we define, because of this proportionality constant, what is going to be a constant is P times the stuff without this minus sign in the exponent is equal to a constant along an isentropically accelerating or decelerating streamline, right? Okay, so that's what we defined as PT, the total pressure or stagnation pressure. All right. Okay, any questions on this? All right, so from this stagnation pressure definition, it's actually pretty easy to go from here to other stagnation quantities, right? So, for example, because we defined, let's actually go to the next slide. So because we defined, because we know that dP over P is equal to gamma times d rho over rho, right? And integrating this quantity means that the P is going to be proportional to rho to the gammath power along this isotropically accelerating or decelerating streamline, right? Okay, and that means a rho is going to be proportional to P to the 1 over gammath power, and P we know that is proportional to 1 plus gamma over minus 1 over 2 Mach squared, and this is minus gamma over gamma minus 1, but there is an additional power of 1 over gamma, which is going to be equal to 1 plus gamma minus 1 over 2 m squared minus 1 over gamma minus 1. All right. Okay, so that's therefore, if you multiply density with this term without the minus sign in the exponent, that becomes what we know as stagnation density, right? So that's rho t. It's definition, right? Because this is a constant along the accelerating or decelerating streamline. Well, you can go further, right? Because we know P is proportional to rho times T. That means the temperature is proportional to P divided by rho, right? Okay, and then we know that the pressure actually goes like this bracket to the minus gamma over gamma minus 1th power, and the rho is to this power. So the temperature becomes this thing times the difference between the exponent on the pressure and the exponent on the density, right? So this is from the pressure, this is from the density. And it turns out after this subtraction, it becomes 1, right? Okay, so the temperature is going to be proportional to just 1 plus gamma minus 1 over 2 m squared. And as a result, to the minus 1th power, so it cancels out and becomes minus 1. So as a result, you can define Tt, the total temperature, being the product of temperature and this 1 plus gamma minus 1 over 2 m squared. Right, so that becomes the definition of the total quantities: total pressure, total density, total temperature. All right, okay, and finally, let's look at something quite interesting along the accelerating streamline. So what is the mass flux per unit area, rho times u? Right, okay, so we know rho is proportional to this guy. So this is rho, and 1 plus gamma minus 1, 1 minus gamma minus 1. Okay, so it's a function of Mach number anyway. And velocity is, of course, the Mach number times the speed of sound, right? So velocity is actually Mach number times square root of gamma p over rho. And we can represent both p and rho also in terms of powers of this little guy, right? So basically what we get is this is going to be proportional to Mach number times, I'm not going to do the algebra too much over here, but it is going to be this guy to some power, right? Because that some power comes from the both the density here and the pressure here and density over here. Agreed? Okay. So what this means is that along an isentropically accelerating or decelerating streamline, the mass flux per unit area actually first, as Mach number goes from 0 to higher, it first increases, right? Because Mach number increases. Okay, but later on, you're gonna see like the primary exponent is gonna be negative. But like as Mach number squared increases further and further, the decrease of this parenthesis is going to overweigh the increase in the Mach number. Okay, and at the end, the unit mass, the mass flow per unit area actually would decrease at higher Mach number. And anybody wants to guess what's the turning point? Yeah?
M equals 1.
M equal to 1, right? That the turning point of m equal to 1 is actually easier to get from the differential analysis we already have done, right? So we actually looked at the last lecture, like the mass flow per unit area. A small change in that actually, depends on the Mach number in a quite interesting way. So when the Mach number is subsonic, this guy increases as you increase the Mach number. As the Mach number becomes supersonic, this number actually decreases as you further increase the Mach number. So that is why as we get to the convergent divergent nozzle, so let's actually start to look at what we have over here. Okay, so this is actually a diagram that tells you how the pressure changes along this kind of a convergent divergent nozzle. And these multiple different lines corresponds to the ratio of stagnation pressure upstream versus static pressure downstream. Okay, so this is assuming that upstream of the nozzle, the width of the nozzle is very, very large. It's much, much larger than the throat of the nozzle. Okay, so that the velocity upstream is always negligible compared to the velocity inside of the nozzle. that is why the pressure is equal to the stagnation pressure, which is equal to 1 over here. Okay, and at the end of the nozzle, you imagine you have a knob that controls what is the static pressure up and down. Okay, so when you have the static pressure almost equal to the stagnation pressure upstream, what you have is pretty much incompressible flow, right? As we have talked earlier, right? Incompressible flow means the change of pressure due to aerodynamics is small compared to the pressure itself. So for incompressible flow, you have Bernoulli's, right? In the throat of the nozzle, you have the minimum pressure, and downstream it rises. Basically, the pressure is going to be monotonic with respect to the area of the nozzle. This monotonic relationship actually holds true for any subsonic flow, right? Because for subsonic flow, the Mach number is going to be monotonic to how much mass flow per unit area you have, which is inversely proportional to the throat, right? Because of conservation of mass. Okay, so, and again, the higher Mach number you have, the lower the pressure you have. That's again something we looked at in the differential analysis. That is why, as long as the whole throat is subsonic, right, we have this qualitative relationship that basically the pressure is a function of the area. So this starts to break down over here when the Mach number reaches 1. So do you remember our analysis that for infinitesimal contraction, the change of the pressure is no longer infinitesimal, right? When the Mach number reaches 1, we have the 1 over 1 minus m. That means the slope, even though at the throat, the slope of area change becomes 0, but the slope of pressure change as the Mach number reaches 1 is not going to be 0 anymore. So the qualitative relationship that as we reaches the throat of the nozzle, the pressure gradient becomes 0, now stops being true, right? We have a sharp corner over here. So this is the critical scenario, and you can actually calculate what pressure you have downstream based on the Mach number is exactly equal to 1 over here. So it's actually a lot of the calculations in turbomachinery is based on that, because in internal flows, right, you know what is the area over which the flow has to go through, right? So from the area and the upstream stagnation pressure, you can calculate what is the maximum mass flow you can push through the throat over here. And from that, the maximum mass flow, you can also calculate what is the pressure you can put on the downstream before the flow chokes. So choking means the Mach number at the throat reaches 1, right? No matter how much you decrease the pressure downstream, whatever happens upstream of the throat will not change anymore. It's going to be exactly the same, which means if you take a probe over here, right, no matter pressure, velocity, temperature, density, whatever, it's going to be completely independent of what you do downstream, right? So the flow has already choked. The information downstream will not propagate upstream anymore. And what happens if you further decrease the pressure is the starting of shock waves forming. And we'll discuss that in the next lecture of what is really happening over a shock wave. Okay, and what do modern airplane designers do to minimize the damaging effect of shock waves, primarily in terms of damaging the aerodynamic performance of airplanes. Okay, so see you this afternoon in the wind tunnel, and then next week.